Okay. Good afternoon, all.
Madam, sir has joined.
Yes, yes, yeah. Raghavan sir came. Yes. Good afternoon, all. Welcome back to the AICT sponsored 6 days short term training program on the topic Trends and Technologies in Antenna Design and its Research Scopes. Now we are entering to the next technical session of today on the topic What we want to know but afraid to ask One Dimensional FDTD by Dr. Rabindra K. Mishra. Professor Rabindra Kishore Mishra is a fellow on the IET and senior member of the IEEE. At present, he is the Department of Electronic Science and Technology, Berhampur University. He has done extensive research in the general area of microwave integrated circuits, particularly focusing on planar antennas. His contributions include applications of soft computing techniques for analysis and design of planar antennas, fractal antennas, metamaterials, and their applications in MIZ and antennas and metasurfaces. Outcome of his research include two new techniques, namely neurospectral technique and neuro-FDTD, in which ANN is amalgamated with spectral domain technique and FDTD method. He has supervised 17 doctoral students and executed funded research projects of more than 1 crore Indian rupees. He received British Commonwealth Fellowship in the year 1999. IET Sir J.C. Bose Burst Application Paper Award in 1999 and Sri Hariom Ashram Predid Harivallabha Das Chunlal Research Endowment Award in 2000. Samantha Chandrasekhar Award in Engineering and Technology in 2008, which is the highest award by the government of Odisha. He was the chair of IEEE AP MTT Kolkata, chapter for the year 2013 and 2014, during which the chapter received Best Chapter Award and Outstanding Chapter Award from IEEE AP and IEEE MDT societies respectively. He has organized workshops, tutorials in USA, France, Malaysia, besides different parts of India. Besides being an associate editor for IJRFM CAE, he is a reviewer IEEE AWPL, IEEE MWCL, IEEE Transon MTTT, MOTL, International Journal on RF and Microwave Engineering, CAD, to name a few. We welcome you, sir, to our STTP program. I hand over the session to Dr. Rabindra K. Mishra. Welcome, sir. Sir, able to hear you? Sir, are you able to hear me, sir?
Madam,
Yes, sir.
because sir is joined.
Yeah, he's joined,
Some
but technical problem. Yeah, technical problem is there. We'll wait for some time. Few more minutes. I think his mic is in muted condition. Perumal, sir.
Sir, respected Raghavan, sir.
Hello.
Sir, our beloved Mishra, sir, has joined. I think problem. Until
I
discussion.
I request our antenna playing person, Dr. Lakshmana Meru, to give your advice to the research scholars. Please, sir. because people are all afraid of seeing antenna. You are a person who are
Okay.
played with antenna. Please give them some advice what not to do.
Okay, okay, thank you. Whenever it is convenient, I will stop it. Just give me 30 seconds time. Okay,
Okay,
for
thank you,
stopping
thank
it.
you.
Right. Just 1 second. I will mute our TV. Yeah. And dear Professor Raghavan Garu, thank you for asking me to just tell dear research scholars and faculty members, there is not much to worry about the antennas. For instance, I was very strong lover of microprocessors in BTech. I'm one of the earliest students to work on Intel 8085 in 1978. Once that is over, when I went to IIT, when I asked my guru, Professor G.R. Babu, late Professor G.R. Babu, he advised me, go to IIT Kharagpur, do microwaves only. Don't do anything else. Because graduation, there is nothing specialization. Then I went to microwaves. First, I felt it a bit difficult, but, with Professor G.S. Sanyal and Professor B.N. Das, just, our Dr. Sudhakar mentioned, we have to go systematically. There are only 4 formulas. Out of that, only most of the time we will be using only 2 curly equations. Out of that, only 1 curly equation only we will be solving for all those things. Nowadays, that problem is also not there. And another thing, this thing is the mindset we have to change. One side we are looking towards IoT, other side, IoT and wireless. Most of the IoTs, of course, within the house you can have wired controls, but wherever wireless is needed, how can we avoid antenna? If it is wired, I can use, coaxial cable or case we can't have at all. So now we need an antenna. All that we need to know is its properties. Where the energy, where the power, how it is spread. So all that is the radiation condition, only 2 boundary conditions. Dirichlet boundary condition, Newman boundary condition. And all these things sir, my suggestion is you must read. You don't have to solve the equations because things are available nowadays. We have finite element method based, method of moments based softwares, and finite difference time domain, finite element just now I mentioned. So many other things are also available now. All that is we have to worry is only what about that, once the wave is transmitted, either it gets, suppose if there is if there is no obstacle, totally free space, it goes up to infinity. That is the one boundary condition. Other boundary condition is current boundary condition on the surface of the antenna itself, right? So once this is happening, that means if there is an obstacle, there is something called reflection. First case. Based on the reflection principle, so much of radar is developed. Now, you say that automatic, auto driving cars and radars for at 77 gigahertz. When one, car is going in front of us and one car is coming behind us, how do we detect this presence? It's the principle of reflection only. How much you worry? So ultimately, we have got false notion that this is very difficult, that is very easy. Nothing is easy in the life. When I was presenting yesterday, now we are going to digital side. Let us say that one of the antenna I told, some antennas 20,000 elements, some antennas are 1,000 elements, some antennas are even up to 40,000 elements also. When the number of elements is increasing, each element we are going to have a software this thing, then software and if your software doesn't work, what will you do? Because you are integrating with the RF microwave chips, because we want mixed signal integration. We have to live with, like the way we are living with corona. Of course, that is a bad example. I don't think so. I don't think it is a good example. But sometimes, see, this thing is MICs and MMICs. MICs and MMICs and more than one chip we are integrating. That's why in DLRL we used in late early 90s and late 90s, we developed a number of, you know, those things. Am I audible? Hello, participants.
Yes, sir. Yes, sir.
Yes,
You are
sir.
audible. Yes, sir. Yes, sir.
Audible, sir. It's
Okay,
clear, sir.
right, right. When one component to other component, what happens? We used to have a cable. At both ends of the cable, there are connectors. Now, there the problem will be there. You see, when these connectors are no more required, we will have some push type of connectors, and we are integrating at that level, chip level. See, that is again, the more you know the RF understanding, you can shine better in the other things, whether it is communication, a radar, or nowadays even in the embedded systems and software. What when you say that computer science, I fully appreciate and I'm happy, but what will you write? You need to look at an example, right? Suppose if we have to analyze a cancer gland. The other day, one from one university, one engineering college, one of the faculty members, HOD, sent me just for advice for this thing, for cancer diagnosis, right? Cancer diagnosis, we need to do something x-ray and as well as so machine learning languages, these things. So once if the x-ray and other things are required to be analyzed, we need to understand about the RF first of all, right? Even x-ray is also of course in the RF spectrum only. So like that, so nothing to worry. Suppose if you take a microstrip antenna, okay, forget about all those things. Now we are looking for the what is that, the digital motherboards. What is the frequency? 2.3 gigahertz, 3 gigahertz. When in 1 gigahertz and above itself, there is a EMI EMC problems are there. Then how are you going to solve them? Just like that, if well, writing a program is definitely required, writing something software is required, but while writing these things, we need to understand. You need not be a designer. You need not be the designer for all antennas, microwaves, but its effect is should be known. Suppose if you go to near to the fire, you know that you have to keep some distance, but you know the properties of the fire, right? Like that, the properties of components. Which component shall I use? The other day, my youngsters are asking, sir, output of the antenna limiter and LNA, I want to use it. Now, why do you want to use limiter and LNA? First of all, you calculate the noise figure of the system. Once you calculate the noise figure of the system, why do you want to reduce the noise figure of the system? Means if you want to reduce, if you can reduce the noise figure of the system, you will have the sensitivity, more sensitivity. More sensitivity means you look for the longer ranges. So like that, once it comes, it means
Sir, you're muted, sir. Audio is muted. Lakshmi Narayana, sir.
Sir.
hello.
Now
Yes,
it is
sir.
audible. Now it is audible, sir.
Yes, sir. It's audible.
Because my see the problem is this, see, this is also wireless, you see
Yes.
that what is it, AirPods.
Yes, 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 sir.
So
Yes.
AirPods, it is wireless. I don't know. You see, from in the morning I charged. I listened to Professor Dr. Sudhakar Rao's speech, and afterwards something. Then again joined for Sudhakar Rao's speech, and again I had a couple of conversations. Suddenly it has gone. See, when we are in the remote, this has gone. So how to improve this? This also patient. If more radiation is there, what will happen? We need to know. Suppose let us say that how to come out, how to understand the properties of, we are talking about 5G, 6G, fine. Now let us say that even without this 3G itself, see number of these things are there, your mobile towers are there, base stations are there, right? From the base station, when the antenna is radiating, suppose somebody just like that, somebody asks, I'm not getting the signal. If 2-3 people in a locality, if they complain that they are not getting the signal, the service provider jolly will increase the amplifier gain. Okay, we are getting the signal, but by increasing the amplifier gain, or should we have one more low power base station? Now, if you are sitting at your home, can you record the received signal from a base station? If a continuous, base station signal in a house, particularly, we say, okay, mobile we keep moving, but what about the base station radiation? It is continuously the nearby. Okay, that also nowadays. Okay, the other day also we were talking about is how to beam farming. When you go for the beam farming exercise, if you understand these things requirement, okay, instead of having my broad beam and radiating to complete a sector place, I will have, suppose when I initiate from the mobile call, right? What will happen if I initiate a call? The call will go to the base station. Once the base station knows from where I am initiating, base station can form a beam towards my side, my locality. Let me say I am in Hyderabad, Tarnaka, and my this thing is there nearby, base station is there. So that base station will look towards my area only. Suppose if it has earlier, if it has got some 40 degrees beam width, it will reduce to only 20 degrees beam width and with a limited power, because once my power should go there and that power also comes here. When I receive the base station power in my mobile says that internally I am receiving this much signal. Based on its mutual communication between the base station and mobile station in the order of milliseconds, base station can manage its power. If I am receiving more power, base station can reduce it, right? So there are, suppose if you follow Professor Girish Kumar, IIT Mumbai, IIT Bombay, he has done a lot of work. I am just only trying to tell whatever his findings are there. There are some reported cancer cases also in Mumbai, cancer cases, or there are some health issues, if not cancer cases. See, cancer case may not directly due to the RF radiation at 900 megahertz or 800 megahertz or whatever it is, but it may definitely aggravate if you have got some other ailments, right? For instance, if a person has got some, what is that, pacemaker. If the pacemaker is there, nearby base station is there, the person will be totally, upset. He cannot manage well. So this has really happened in Mumbai. What happened, Saas Bahu ki case tha. Because once, a software engineer, his mother came and he was very happy that his mother is coming to his and to looking at. And, the next day, mother was a little bit, upset and unhappy. He said, "What happened, ma'am? What happened?" No. She was not telling, because it cannot be. It is not like a temperature, cough or something like that. He thought that it is a saas bahu ki problem, son-in-law, daughter-in-law and mother-in-law's problem, right? So with these problems, what has happened? So due to this, one day the son was also really, mother is still suffering, so there could be something else. He took to the doctor, and doctor saw, all her parameters are good. She go home. Then the next day also the doctor saw, the mother was very uncomfortable. Again he took to the doctor, but that the doctor is, in the morning, speaker was telling that medical people are also becoming a little bit RF oriented people. The doctor has asked, "Look, gentlemen, where are you living?" "I am living somewhere Andheri, Vagara in Mumbai." So, okay, nearby, do you have any mobile base station nearby your house, flat? "Yes, sir, there is one near within 100 meters. One base station is there. That I don't know. It looks towards my flat or something like." Then he told, "Okay, your mother has got a pacemaker. You are well within the 100-meter zone. So your mother will face this problem." That means whether the doctor is a macro engineer, is he designing, has he studied Maxwell's equations? No, not necessary. This is all common sense problem. So the moment you know, that means what is there? There is an antenna. microwave power radiation. But as an engineer, can we not help it? We can definitely help them. Earlier, in the first generation mobile communication, we were having, antennas, what is it? Vertical linear arrays, right? Vertical linear array. See, one dipole will give us, what is the pattern is, omnidirectional pattern, and what is it called, we will have a 30 degrees or 78 degrees the elevation beam width, but that much we don't need, and its gain is only 2.15 or 2.6 maximum, that gain, but we want more gain. What will we do? We will stack one element over the other. That means we become vertical linear array. By doing this, still we have what? 360 degrees beam width, and elevation beam width is reducing, because elevation beam, the aperture perpendicular to the aperture, that the beam width reduces. Then how much beam width we reduce, that depends upon our design. That's where we are required. It is not a very great thing nowadays. Take a particular any software package and do it, but all that thing is, an RF engineer should be friendly with a mechanical engineer, right? Now on this antenna, once everybody does this, I think in the morning session I heard couple of, I think more questions are there. Sir, can I publish only simulated results? What is the purpose of simulation? Is it only to put a paper and get the shabashi and this thing? No. What is our intention of simulating is, we want to design an antenna and realize an antenna. Let it be microstrip antenna or any other antenna. Like that, once you do it, why the simulation is done? How the simulation tool is helping? Simulation tool is helping because it is very near to the practical results. Otherwise, what we were doing, see, in 1980 to 83, I developed a element to the 16 element phased array, linear phased array. That, see, for IFF, because this is a known, I can disclose the frequencies also, because this is known. IFF means identification of friend or foe. It transmits at 1030 megahertz. We need only just 5 megahertz or 10 megahertz bandwidth, and it receives, transponder receives at, transponder receives 1030 megahertz, and transponder replies at 1090 megahertz, right? So we need to have, those days, still things are there, but dual frequency, fine, we can have it. There are other things, the problems are there. Then we wanted to have from the same aperture, we wanted to have the, so simple microstrip antenna does not give the, that much of bandwidth, 1030 to 1090. Okay, doesn't matter in between. So we could have dual frequency, but there are some, this type of tools were not there. Then we have gone to a folded dipole element, printed folded dipole element. Then, okay, that is also not our invention. One author was Dubost, because that's what, Dr. Sudhakar was also telling. Do the literature survey in industry or in R&D. Of course, ours is applied R&D. Okay, this was good, so we have taken the Dubost dipole element, and it took about 4 iterations for me, because first we did it, understood, constructed, it was not working to the satisfactory level. Then change, because whatever, see, one question also was also there. Can I do some cut and trial simulation and publish the paper? That also we heard it. Yes, cut and trial you do it, but paper may not get published, but still it is useful for us for the realization of an antenna. So like that, instead of using the 4, so using 4 iterations, nowadays we are getting in first or maximum initial attempt, then final. That is where it is coming. With this, once the aperture is same, aperture size is same. Let us take a horn antenna example, which Dr. Rao was also telling. Most of the people are behind only microstrip antennas. Suppose if you take an aperture antenna, for a given aperture, let me say 8 into 40 gigahertz. Okay, all of you are available about the whatever is going in the laboratory. That is fine. The microwave laboratory. If I take 8 into 40 gigahertz, or 8 to 18 gigahertz, or 2 to 4 gigahertz, anything 1 octave. We call, if the frequency is F1 is equal to 2 gigahertz, F2 is equal to 4 gigahertz, 4 by 2 is 2, that is called 1 octave. So But suppose if you take X-band waveguide is WR90, the model. So WR90, that is approximately 1 inch by half inch. Broad dimension is 1 inch, narrow dimension is half an inch. That works between 8.2 to 8 to 12.4 gigahertz approximately. Okay, little bit this thing. So 8 to 12.4 means hardly, but I want, I want 1 octave. How it happens? Then we need to introduce what? In a horn antenna, we need to introduce some ridges. Ridges, what the ridge does it? Ridge means, suppose in the bottom wall and the top wall, we introduce some sort of metal strip ridge that reduces the capacitance, right? So capacitance has that is the fundamental principles. So that means if our fundamentals are strong, we will enjoy the RF and microwave work. Those whose fundamentals are good in the digital flip-flops, counters, gates, microprocessors, they will really love the digital work. Like that, if we have this, but at any time, because from the fundamentals of science in the beginning, even 10th class, up to most of the people are appearing for IIT examinations, and that level of physics is good enough to understand microwaves. First and foremost thing is bent of mind. Mindset we have to change, because most of the people we are about higher salaries, I do know. But salaries are better in definitely in the digital area, right? But there the tensions are also equivalently good, right? High risks are there. I think one of the audience is Dr. Runa Kumari. She happens to be from BITS Hyderabad. We all work together in for IEEE Hyderabad section, right? So this is where I think I felt that I should talk to you. Raghavan Sahab, anything still you want me to continue? Or Perumal Sahab? Hello?
Perumal sir.
Shall I continue?
Yes, sir.
Yes,
Yes, sir.
Yes, sir.
Very informative. Very informative.
Very
Informative
informative,
session,
sir.
sir.
Please, sir. Please, sir.
Yeah, because that our next speaker, our Professor Mishra, was supposed to speak now at 1:30.
Yeah, sir. There is some net issue. Sir is solving
Okay.
that technical
Okay.
issue. Within
Okay.
5 minutes,
Okay.
sir will join, sir.
Sir, and
Okay.
Please
also
help us.
Whenever he joins, actually I joined only to listen to him.
and also your practical experience in that DRDL antenna
Yeah.
fabrication, that and all one cannot get from the books. Only you can
Okay.
tell.
Okay. Right. Okay. Now we have to find why do we need antennas? Again, I told you. Suppose since I think my experience is with electronic warfare. For electronic warfare, see, for communication, we know the transmitter and receiver both know each other, both frequency is known. Transmitter knows the receiver's frequency, receiver knows transmitter frequency be at the time of transmission, because if it is a line of sight communication, they will align and keep it. But let us say that we are at the adversary's border. Let me say at Pakistan or somewhere. We do not know. See, anybody first requirement is the communication, second requirement comes the radar. First of all, somebody has to give some instruction. Okay, look, gentlemen, go there and park the radar there, and they will inform the logistic people. Isko khana pina, so whatever food, some. So that means some communication goes on. When such communications goes on, we have to intercept the communication. Now, in the intercept in the communication means communication can be done with HF, VHF, UHF, even at the lower band of L band of microwave also. Then how do we know how many antennas we can keep? So we can keep. So any frequency we should be able to listen. That means we need a very broadband antenna, right? 30 megahertz to 100 megahertz. It looks only, let me say, 30 to 100, 110. Suppose 108 megahertz, there's 90 megahertz, this other transmissions go on, right? It looks only 70 megahertz for me. 60 is one octave, 60 to 110 is another octave. Such a huge bandwidth, will we be able to get it? So that is the another challenge. But still we get it. Then there also we use monopolar dipole, right? Then what is the case? One side we are telling, all the books refer that dipole is a resonant element, right? Now, if you see that in the Stutzman's book, in the very first chapter itself or anywhere, when you reduce the small, in small dipole will have almost, omnidirectional pattern and good this thing. Now, this omnidirectional dipole, where we are part of it. Once if you keep on reducing the size of the dipole, right? No doubt, it resonates at one frequency, but other frequencies also it receives, but at very, very low gain. Can you believe? In one antenna, so in antennas, in particularly communication antennas, we get up to minus 23 dBi gain. That is the way. Suppose, then why that should be minus gain? Suppose if I want at 900 megahertz, I will design the length at around 800 megahertz or 850 megahertz. At 850 megahertz, I'll get good gain, or 700 megahertz. Upper, that is the trial and error method. Then for all the other frequencies, it will happen a small dipole, right? Small dipole, not the lambda by 2 dipole. So when it comes to smaller and smaller, what will happen? Now 1.5 meter length antenna, if I can I have it on my feet back? A person has to carry. Now a person has to take that TR set, trans receive set. So such problems will be there. So we have to reduce the antenna, and gain we have to get somewhere else in the amplification, LNS for receiving, right? And we have to pump more power. What can you do? It is unavoidable, right? When coming to the radar side, let me say, suppose we want to find, again, measure the frequency, unknown frequency, we do not know. Suppose the radar is radiating, looking towards our border, let me say. Then where it is, at what frequency it is, we don't know. From what direction it is coming, we do not know. So first what we do is, we design one antenna which works for 0.5 to 2 gigahertz, one antenna, 2 to 8 gigahertz, 8 to 18 gigahertz. All these are biconical antennas. Because one biconical antenna, we cannot have it. These 5 gigahertz to 18 gigahertz, I will be able to intercept. Right. But how do I know from 0.5 to 18 gigahertz, this is the frequency? Because nobody will tell the frequency. That means there is a method of, suppose you receive a frequency, delay it and correlate it. We will get a approximate the frequency size. That is what frequency measurement of unknown frequency. In the laboratory, in the microwave laboratory, we are measuring the frequency. First of all, charge will tell that we know that it is, we are using the what is it called, Klystron source. We know it is where its frequency is. Then we rotate that and, oh sir, I got the frequency. But if nobody tells the frequency, this is the method. That means instantaneous IFM receiver, instantaneous frequency measurement receiver, DIFM, differential digital instantaneous frequency measurement. So that is the other part of it. Coming to antenna part of it, that means we should be, that is omnidirectional antenna. From wherever it comes, its gain will be around not more than 2 to 3 dB, or maximum 1 to 3 dB. It won't do more than that. Now, we have to find the direction. How to find the direction? Then I use more than one antenna. Let me say I'm using 4 antennas. One antenna is looking towards east, west, south, north. When any waveform comes, I compare the signal received from these 4 antennas. Right? I know the patterns in advance. Right? I know the pattern. So with these particular things, I will compare whether east antenna is getting more signal, west antenna is getting more signal, south and north. Based on these things, approximately I get means I will compare the amplitude. Again, here also we need broadband antennas. At least once the frequency is known by frequency measurement receiver, we will have the DF antennas. One DF antenna is something like that spiral antenna, right? Now, technically speaking, spiral is a Archimedean spiral. Let us take it. Archimedean spiral is the very frequency independent antenna if the size is good, right? Then, why are we making it a cavity backed? Because the spiral is a bidirectional radiation, right? Spiral is a bidirectional radiation, Archimedean spiral. We don't want the reverse radiation. We want only forward radiation. Then in the forward radiation, can we not keep just one plane or ground plane? No. Then it becomes resonant. Then we make a cavity type of thing and put some absorber inside also to absorb. That means half of the lobe we are eating out, which is going to the other side. So that is the reason spiral antennas also will have lesser gain, particularly at the lower end of the frequency. No surprise up to, see, 5 to -7 to -8 dB also, because we have crunched in just in 2 inches diameter, we have 2 to 18 gigahertz spiral antenna. At 18 gigahertz, fine, it will have 2 to 3 dB. But it comes to 2 gigahertz, it will be having -7 dBi. So negative gain, don't get afraid of it. There is a negative gain is also possible. It will be there. First, after going from the college, I also wondered why an antenna should have a negative gain. And we also told that in the definition of the gain is that how much power we are giving to the input of the antenna and how much power it is pumping out. Whatever we are giving, half of the power itself, we ourselves are making it to absorb. So obviously the gain will not be good for such antenna. So just now I told, one east, west, south, north. This is amplitude comparison, right? Amplitude comparison. Based on that, we will find out from this direction the signal is coming. But this is not accurate. This is the direction of arrival. DF accuracy, direction finding accuracy is about 6 degrees. Then what will be the RMS? Will go to maximum error. RMS is 5 to 6 degrees. Then that will be there about 15 degrees the peak error. What will we do? Suppose with this peak, but then will it be useful? Yes, it is also useful somewhere. Where it is useful? Not on the ground. Lesser. It will be useful in the sky. Because there the people want in the beginning 1970s to even 2000, they want in that whenever for the radar, for the in the EW equipment, what will happen if some radar is looking towards you, right? When the radar is looking towards you, this is only a beaconing. It will only give a warning to you, some radiation is there. Then what is your requirement? Just go away from that. Don't venture. If you want to jam that fellow, then you need a accurate direction. In the accurate direction finding, you go to phase direction finding. Phase means 4 elements you take. Then from the 4 elements you derive from that, this is we called baseline interferometer principle. We all read these things from high school. I don't know why we are afraid of using these things. So with the phase interferometry principle, we will find to the extent of 1 degree accuracy over the full band of 2 to 18 gigahertz or 8 to 18 gigahertz. But if you want a very, very narrow beam, means about 5 to 6 gigahertz, within that frequency means you can even have 0.1 to 0.2 degree, 0.5 degrees accuracy also. Now, what does this mean? If this accuracy is there, if you tell, because ultimately what is our intention? We have to, in the enemy zone, we have to fire a missile to tackle that. If you fire a missile, crores of rupees, you can't just like that fire like a gun, machine gun or something like that. So for that means, the moment we find a radiation, first thing is we find the frequency. Second thing is we find the direction. For frequency finding, we need an antenna. For direction finding, we need antennas. Then we will communicate to that fellow or the missile fellow. So this is upright direction. There also on the peripheric circumference of the missile seeker, we have an antenna, seeker antenna. Because during the flight of the missile, right, that it also looks for the target approximately, it maneuvers, because suppose if I tell 1 degree accuracy means 3 degrees peak power, it may go it may miss the target. So while in the flight, missile also gets the coordinates corrected. There also then radiation is required. That is the design, defense part of it. Now hello, just 1 second, please. Hello. Sorry. See, suppose then where the issue comes straightforward only when the design is there. Why do we need so many antennas, so many places? Dr. Sudhakar Rao also told, if it is a satellite, we have to keep the antenna, means temperature excursion. Right, it has to work. Then if I want to keep it on the ship, that's also fine. Ship does not have any restriction for the weight and size, but the restriction is on the ship, number of antennas are there. Right. The other thing is for the aircraft has got more than nearly 50 to 70 antennas are there. Our own aircraft, for this thing is AWACS aircraft, AEW and C aircraft, for which our Dr. Christopher was program director. He was the chairman, earlier chairman of DRDO, right? So for that we have a phased array. Whatever, because normally when we talk without the permission of the certain laboratory, because since we don't normally use that material directly, because we need clearance to tell. But if it happens, if it appears in the internet, we will take from that and we can tell it. Since now it is more or less it is available, there we use a phased array. That phased array is almost a linear type of Hello. Is Professor Mishra back?
No, sir. Continue, sir. Please, sir.
Continue, sir. Please,
Okay.
sir.
Okay. Once, if suppose, let us take one IL-76 or something like that, one big aircraft. Even Boeing aircraft also does not matter. When one of the systems we have mounted on the Boeing aircraft, we call that system as a catcher. Of course, that is decommissioned so that we can talk. What will happen is, now, see, I was telling something like that, strategic and tactical. Now, lot of things we are doing, drones and other things also. Before these drones and smaller things, what UAVs, what we used to say is, we used to say airborne early warning and control systems. In the airborne early warning and control system is there, then we fly an aircraft at a almost reasonably high altitude, so that it can see almost 400 kilometers into the adversaries. This thing means at least 260 to 400 kilometers, whatever is radiated, it can collect the information silently, right? So that is the area of one this thing is. But sometimes that is only EW part of it. But who will tell? If that radiate only, we will come to know. But if they don't radiate, we don't know it. So another deliberate equipment exercise is radiate and try to know it. Means from the reflection. So good big phased arrays have been developed by CAPS, Center for Airborne Systems, with LR. Actually, designer is LRD, Radar and Electronics and Radar Development Establishment, where Professor Dr. DC Pandey, I think most of you must be knowing. So then, what is the issue of this thing? Suppose you say that when you were research scholar, when your guide and your principal and somebody is there, will you be able to talk very freely, whatever you see, some throat choke will happen. Even this is a physical point of view. We won't be able to be so free in the company of others. Now, what is that? In the one element transmits in the presence of other elements, again, that is a coupling. So this coupling is not only for antennas, it is for everywhere. That means we need to study one incident, one radiated wave, rest incident. If all are radiating and all are receiving, that is a very complex problem. We need to tackle these problems. Now, let us say that we want 50 billion IoT devices are going to required, right? 50 billion devices are going to come, right? Then sometimes we know that PCB antennas are required. I think antennas for what is that, medical applications. Where antenna is not required, you tell me. If you use mobile antenna is required. When you use for every application, wherever the wireless requirement is there, the antennas are required, right? I think my advice to scholars, research scholars, are and encouraging the guides, supervisors. First of all, my sincere advice to the faculty members is, please do not scare the students. First of all, they say, oh no, it is very difficult subject, you have to work hard. No, it is not difficult. Make it easy. See, one after other, if you see this, you take Stutzman and Thiele, one book is there, how once you take two dipole elements and keep the distance between them and see that grating lobes are coming, the same thing is happening in the communication systems also. When you study Fourier series, you get number of, this thing comes into 2 pi, that is where we start. Period is 2 pi or 1 over t, then we keep starting. So this is a spatial, that is temporal, right? Now, I think, Professor, shall I take some questions? This is
sir,
what I felt.
Sir, excuse me, sir. Sir is ready. Mishra sir is.
Okay. Then thank you.
Thank you. Sir, thank you for your support, sir. Thank you for your wholehearted support in the hectic situation. So thank you so much. Thank you, sir.
Very nice extempore talk. There are 2-3 scholars, and like as you told, Dr. Runa Kumari is here. Maybe afterwards they will pose a question. I understand Runa Kumari is secretary, while you are a chairman of the IEEE chapter also. So your talk will go a long way.
She's very active and she organizes a number of very good, I think 3-day or something like that, national symposium, but it doesn't look like national. It is the more than international quality. She has got a lot of flair towards antenna design.
And to my knowledge, she is the only lady secretary in India, I think, in IEEE.
No. Earlier, Madhumita Chakravarti was in a chapter chair also, MTT, Microwave TV Techniques.
Secretary-wise, in South
Secretary-wise, yes, she might be first or second. I think Bharati did it once. Ananta Bharati. She was my PhD scholar earlier.
Anyway, nice that instead of PPT, you talked directly to the mind of the 70 participants. Thanks a lot.
Thanks, Professor Raghavan. Thanks, Perumal Garu. And it's my pleasure. It's my
thank you, sir. Thank you. You have to tell the thanks, sir.
Thank you.
Thank you, Dr. Sir. Thank you, Dr. Lakshminarayan Mergus, sir, for sharing your very valuable knowledge. And Raghavan sir already said we can't find this valuable information in any book. It's very true, sir. Thank you, sir.
Thank you.
I'm muting my speaker, right?
Yes, sir.
Right.
Okay.
But I'm there on the line.
Okay, sir. Thank you, sir. Thank you, Raghavan sir, to recommend the name of such an eminent personality like Lakshminarayan sir. Thank you, Raghavan sir.
Thank you.
Madam, please invite.
Okay, yes, sir. We welcome Professor Dr. Debindra K. Mishra to our STTP program, and over to you, sir. Sir, am I audible, sir?
Yes, madam. You are audible. Am I audible?
Yes, sir. Yes, sir.
Okay. Okay, thank you.
Please welcome the Sama.
Uh,
Yeah, welcome,
Dr.
sir.
I think there is no need of welcome now. Last two times I have been there. Let me at the outset take excuse from everybody, each one of you, senior people like Professor Raghavan, Professor Narasimhan, uh, everyone, Professor Mahadevan, everybody has to wait because of me. Uh, I had some problem. From yesterday, I used to get problem with my audio, and today suddenly everything went off. I have to set it up. Now I am using two laptops. In one laptop, I am presenting. One laptop is connected to audio. So I have to arrange another laptop. That is why it took some time. Otherwise,
Okay,
I
sir.
was ready in time. Unfortunately, this was unavoidable on my part.
Okay, sir. It's worth waiting, sir. We will wait
No,
even days.
no. One should not wait. The time is very important. We should stick time. Unfortunately, I could not do that. I'm very sorry for that. I beg excuse of everybody, all participants, all eminent speakers, everybody, all organizers, organizing committee members. So please forgive me for this. Let
Sir,
me.
no need of forgiving, sir. We have utilized this time. We are
Uh,
fortunate to wait for you. This is Lakshmi Narayana.
Dr. Lakshmi Naru has given a
Thank you. My heartfelt thanks to Lakshmi Narayan sir. You managed the show in this period. Thank you so much.
Right,
Okay,
sir. Right, sir. Please go ahead. Please go ahead. Right, sir.
let me start what
Yes,
I intended to discuss with the participants. This is particularly aimed at research scholars, mostly research scholars, maybe some teachers or professors. What we do usually, why I have chosen this topic, as we go through the topic, you will gradually understand why I have taken this topic and why I have taken this name, what we want to know, what afraid to ask. Reason is, okay, before that, please tell me, is my PPT visible?
yes, sir.
Yeah,
It's
sir, it
visible,
is
sir.
visible.
Visible.
Uh,
Okay.
Please put in
Sir,
slideshow.
yeah, put it in slideshow, sir.
No, it is in slideshow. I have not started changing. So it is in the past slide only. So once I go to the second slide, I will ask you if it is changing or not. Okay, the reason is nowadays a trend has started among research scholars. Most of the research scholars that we start simulating using the available commercial packages or free packages and do some simulations, come back to the guide or supervisor, then I show them that, okay, sir, I have got very good results. My results are excellent. And when they go for fabrication, there is complete mismatch. The results just blow away. Why that happens? Reason is we do not know. Mostly people do not know what they are doing. They are just making a structure, giving some source, some input, excitation, and then simulating it without knowing what is going on inside, how it is functioning, and what are the problems with any of the packages. I chose the topic of FDTD because it is uh, comparatively easier to understand the physics or to understand what happens within the domain. So that is why I have taken FDTD. Otherwise, the concepts that we are discussing, I am going to discuss initial part. Those concepts are applicable to all softwares, all commercial packages that we are using in our labs for the students. Now, we should understand what we are doing. Then, if we are compatible with the package and if you find that the package can solve our problem, then use the package appropriately. Uh, so let me start with some assumptions. Is it visible? Second
Yes, sir.
slide is the
The
slide
first,
changing?
Yeah, it's first slide, sir.
First slide, some assumptions. It
Yeah.
is written that some assumptions. Is it correct? Am I correct?
It's
The title is
the
title is
title.
there.
Title is there, sir.
Title is okay. Title is there.
Yeah.
Okay, and the assumptions. What are the assumptions that I am going to make? First is the formulation that we will see or that we will examine are for non-dispersive media. So medium is not dispersive. Although I am considering FDTD, there are methods of modeling dispersive media because dispersive media is basically frequency dependent media. So if it is a function of frequency, take inverse Fourier transform, go to the
Sir, excuse me, sir. Sir, sorry to
yes,
interrupt you. I think you are
yes,
not. You are sharing the other screen, sir. We are still seeing this title slide, sir.
title slide.
Not the assumptions. Assumption is second slide, but we are
Yes.
seeing still first slide. First slide, sir. Can you share again, sir? Can you
Okay,
press the
okay.
share
Let me
button
try.
again?
Let me try. Let me try.
Okay, sir. Sorry, sir. Thank you.
Java.
Now it is okay, sir. Now it is
Yeah,
okay.
now it's
Now
okay, sir.
Now I will go to the presentation mode. Presentation mode.
yes.
Now is it okay?
Yes, sir.
It is okay.
It is okay.
Yeah.
Let me change the pro size. Then I will come back. Then I will start. Change. Is it changing? Or it remains as some assumptions?
Yeah, it's a second slide, sir. Some assumptions.
No, I have gone to the fourth slide. So it is not changing.
Yeah, it's
Sir,
not
sir,
changing slides.
sir, sorry to say this. Sir, there is a one play button is there. Can you press on that, sir? On the right
Yes.
bottom.
Yes, I am doing
Right
that.
bottom.
I am only playing. I am only clicking on the play button. But it is
Okay,
not
okay, sir.
working. Now it is changing. Now you
Yes,
can
sir.
see.
Now it
Yes,
is
sir.
changing,
Yes,
sir.
sir.
Yes.
Okay,
It's
so
changing,
I will
sir.
not go to the presentation mode. I will show my slides one by one. I think that will be better
Okay,
if I
sir.
go that way. Okay. So let me start with some assumptions. The first assumption is the media will be non-dispersive. The media that we consider or examine will be non-dispersive in nature. We can do dispersive media. What we have to do is dispersive media is frequency dependent. Go to the Fourier domain, take an inverse Fourier transform, come to find out the time dependency. Then we can then it will we can model the dispersive media. But for simplicity, I will consider only non-dispersive media. I will leave out dispersive media. Then the domain under consideration will be bounded. So we are not having an infinite domain, although it is possible, infinite domain is possible, but for simplicity, again, I will keep myself limited to bounded domain. Third is the numerical scheme that we'll employ is up to fourth order approximation. So it can be second order approximation, third order approximation, or fourth order approximation. So depending on different conditions, I will go to the different approximations, but maximum will be fourth order approximations. Of course, one can go beyond fourth order approximation, and we can see what is the effect of that. That we'll see later. And I will restrict myself to Cartesian coordinate system because that will be easier for understanding of most of the scholars. Then I also assume that most of the participants have some exposure to MATLAB, minimum exposure to MATLAB. Once or twice they have used MATLAB, minimum exposure to MATLAB. And I will be happy if you have MATLAB with you. Get ready with MATLAB so that you can do some examples, simple examples that we are going to check that you can do hands-on, you can do as we progress with the lecture. I actually requested earlier to Professor Shankar to intimate participants. If they intend, those who are really interested, they can use that. They can use MATLAB. And of course, all of us being from science and engineering background, we know what is Taylor expansion, and we have some knowledge of differencing different equations, differencing those things we know. So these are my assumptions. After these assumptions, let me go to some two forms of considerations that I am going to take up. One is the integral form, other is the differential form. When I say integral form and differential form, I actually mean the Maxwell's equation. Integral form of Maxwell's equation or differential form of Maxwell's equation. We know physical insight at each point of the domain can be obtained if we go to differential form. The reason is when you differential form always includes a differentiation. Now, differentiation is always mathematically, differentiation is always at a particular point. Therefore, inside the domain, go to any point, take a differentiation, you get the knowledge or get your physical insight into that once you do the simulation at that point using differentiation. So that is one advantage with differential form. Then we know the differential form, there is a problem and advantage both. It is controlled by the boundary conditions. Now, the differential form of Maxwell's equation in their exact form are not applicable on the boundary. Boundary will be given a boundary condition. So they are not exactly applicable on the boundary. I'll come to that just a second later. But they depend within the domain how the field will behave. That depends on how the field is behaving on the boundary. So these differential forms are dependent on boundary conditions or they are controlled by boundary conditions. And these models are unbounded. Models are unbounded domain. Within the domain, they can be made unbounded. There is no bounding for the models. There is no bind on the models within the domain. Within the domain, the model can be anything. We can use any form of the model. That we can do easily. If we look at on the other hand, if we look at the integral form of Maxwell's equation, we get physical interpretations from integral form also. But this gives you the holistic interpretation, not a point by point. Every point, every location, you cannot get any interpretation using the integral form unless your closed loops are very small, in which case they actually gradually convert to differential form. So you take a closed loop or closed surface. So over the surface or over the loop, we get general or average, on average, how the field is going to behave. So that is possible with integral form. The advantage of integral form is we always get the boundary conditions. If there is a boundary, the boundary condition, we can always derive from the integral form. It is almost impossible with the differential form. It is very difficult with the differential form. Easily we can use integral form to derive the boundary condition. And in all textbooks that students refer or research scholars refer, they find this. The boundary condition is derived using integral form of the Maxwell's equation. That is where integral form is most important. And it is relatively difficult to model unbounded domain. Domain has to be bounded because you have to have a closed loop, or closed contour, or closed surface because of the form of the integral equation. That is not required in the differential equation. So they need not be bounded. Now, when I said this, I also said that this differential equation, differential form that contains a differential equation. A differential equation, we know, we can divide it into two categories, broad categories, two broad categories. One is ordinary differential equation, other is partial differential equation. Ordinary differential equation requires an initial condition to get an exact solution or closed form solution, it requires an initial condition. And it is easy to solve. Most of the ordinary equations, ordinary differential equations have been solved. There are very few, more than 95% type of ordinary differential equation have been solved by mathematics and mathematicians. So there is very few which is remaining where people require computing or computers or take help of computers. Otherwise, it is easy to solve. Whereas on the other hand, on the PDE, partial differential equation, uh, uh, initial condition can be there if it is a time dependent thing, but there will be always a boundary condition. Because the domain has always a boundary. The boundary may be at infinity or maybe at finite, but the domain has a boundary. So you will have a boundary condition. The moment we say boundary condition, every point on the boundary, if you consider behave differently, which means on the boundary we can, in theory, not in practice, in theory, we can have infinitely many solutions on boundary. Accordingly, the solution within the domain or behavior within the domain will change. So that is one aspect in PD. Therefore, because that is the condition, it is difficult to solve. The solution of PD is difficult. Historically, if you know, this ODE goes back to Newton. He used to use ODE for studying planetary motion. When he was studying planetary motion or planetary laws, he was deriving his planetary laws. He used ODE, that is the source of ODE. It goes back to Newton. Whereas PDE, the source goes back to continuum mechanics. So it came much later. The partial differential equations came much later, so there is a lag, time lag. That is why maybe most of the ordinary differential equations are solvable. Most of the ordinary partial differential equations are not solvable. So you have to take help of computers or computers. So with this introduction, let me do a rough condition, very crude method of conditioning, which may not be acceptable to many of you. So let me do a rough condition. The conditioning is, just give me 1 minute. So I do a sort of very crude rough conditioning. Let me start with one of the Maxwell's equations. The let me start with this Faraday's law. At least let me start with Faraday's law. So in the Faraday's law, I am taking one component only. So since I will consider 1D equation, I am taking one component only. So the component will be dou Ey by dou Z is equal to minus dou T Px. This we know. So Ey and Px, they are perpendicular to each other. They are orthogonal to each other, so they will be divided by this equation. So if it is a 1D propagation, the direction of propagation is G. My electric field is Ey, magnetic field will be X, Hx. So for that, this is the equation dou Y and dou G of Ey is equal to minus dou T of Bx. Bx we can write as mu Hx. So take mu outside. Then for mu, write root mu into root mu. So that is my mu. Then multiply root epsilon, divide by root epsilon. Then what I will get is root mu into root epsilon, that into root mu upon root epsilon. Root mu into root epsilon is 1 upon c, so 1 upon v. V is the velocity. In the medium, if it is free space, it will be c0. Otherwise, it is v1 upon v. Then root over of mu by root epsilon is eta. It is free space impedance or impedance of the medium. If it is free space, it will be eta 0. So we go up to that. Then I'll keep 1 upon v outside, take eta inside, multiply that with hx. So dou t of eta hx. Now we know the relation. Ey, it should be, so should be eta. Therefore, Ey should be equal to eta hx. So for eta hx, let me write Ey for the time being. So if I do that, what I lost is, I lost information about h, but I get everything about E. So for the time being, I will be here with that. Then I will come back to h. I will definitely have to use h. So that I will come back. But for the time being, let me drop out h and stay with Ey. So my equation, Maxwell's equation now comes to this form. Dou t Ey is equal to minus v dou z Ey. Now, as you know, if you look at this, this is an equation of a wave, not a complete wave equation. This is what people in physics and mathematics, they call it a half wave equation. Your wave equation should be dou square t Ey is equal to minus v square dou square z Ey. But people call this equation as half wave equation in the field of mathematics and physics. I have read some of the books of mathematics and physics from where I have borrowed this idea. So this is half wave equation, not the complete wave equation. But the behavior is same. It is a wave propagating and it is propagating away because of negative sign. If it is a positive sign, then it is coming towards the source. So it is a wave propagating. Now, next two equations, you know, we are very conversant with these two equations. Taylor series expansion of Ey. Ey is g plus delta c and Ey g minus delta c. What is the difference between them? And the difference is in the first equation, all terms are positive. In the second equation, all even terms are negative. But the form is this. Now in this, please remember, dou g means dou upon dou z. So d by dz. Dou gg is dou square by dou g square. So that is the second derivative, third derivative, fourth derivative, fifth derivative, etc. So number of g keeps on increasing according to the order of derivative. And I have truncated it. So where I have truncated it at the fifth term, therefore the order is delta z to the power 5. So if I truncate it at third, then to the power 4 or 3, so that is depending on my requirement, I can truncate it at any place. Yes. So now, once I know this, let me formulate a finite difference key for this equation. Dou t Ey is equal to minus v and dou z Ey. So for that, I am going to formulate the equation. Okay. Let me ask if there is any student one question. The question is, when we are in pre-college, we said that the derivative dy by dx, by definition, when we started learning calculus, dy by dx is equal to limit delta x goes to 0, delta x goes to 0, delta y by delta x. We never asked what is delta x, and when it says delta x goes to 0, how close it is to 0, and when we will say that delta x is equal to 0. So that was a question which most of the students avoided and never tried to know Either they never tried to know, they were unconcerned, they accepted it as it is, or they were afraid to ask it. So while we'll consider this, we'll progress with this. Gradually, we'll know what value of delta x we'll consider to be approximating to 0 for the problem at hand. It is not fixed for all problems. That much I will tell now. That delta x approaches 0. So the value of delta x is not fixed for all problems. For different problems, it will be different when we are going to do numerical analysis. And the definitions of delta y, delta x, those you know, delta y is value of the function at between 2 points at x2 and x1, difference of that. And the 2 points are x2 and x1. So exactly in between them, delta y or dy by dx is there. So let me come back to my equation. My equation was my equation contained the term dou z d and dou z ey and dou t ey. I am not concerned right now with dou t ey. I am concerned with the finite difference, not the time domain technique. So time domain, let me keep it as it is. I'll deal with it later. But for the time being, let us look at what happens with the finite difference. Then we can extend that idea into time domain. Same process, same thing. Everything will be same. So you can extend easily. So once we know finite difference, it is easy to learn what is finite entity. So dou z ey, let me write is as approximately equal to a ey z minus del g plus b ey ey plus c ey g plus del g. Now, why I am doing this? I am doing this to find out what will be my derivative at a point g. And I assume that since by definition of dy by dx, I know that it depends on two sides, x1 and x2, similarly g1 and g2. So it depends on its neighbor. So where you are going to find it out, it depends on its neighbor. Either that point and its neighbor, immediate neighbor to the right side, or that point, immediate neighbor to the left side, or that point and the neighbors on the right side and left side. So let us take all the 3 points. That point is EYC at that point. To the left is EYG minus delta G. To the right is EYG plus delta G. And we multiply some coefficients so that we can calculate the value of coefficients. This is an approximation. Since this is an approximation, so there will be a truncation error. The first term is AEY G minus delta G. Then that will be equal to, now let us EY G minus delta G, expand that in Taylor series and multiply that with A. So that is the right hand side. Then the second term is B EYZ. So B EYZ, write it. It will be remaining as B EYZ. EY G plus delta C. Again expand it in the Taylor series, multiply by C. So that will be the right side of the third line. Then the fourth line is I am taking the difference. Truncation error is the difference. So the fourth line is the negative of the RHS side. So RHS, sorry, negative of the LHS side. LHS I have taken to the right side. So that will be minus dou z EY. That is approximately equal to minus dou z. With that remains as it is. Now to find out these values, what I need is on the right hand side after the equal to sign, on the 3-4 lines, look at the terms and after the equal to sign. If it is truncation error has to be 0, then the first column has to be 0, which means A plus B plus C has to be 0. Second column has to be 0. So minus A plus C is to be 1 upon delta C. Third term has to be 0. That gives me A plus C is equal to 0. So I have got a matrix form. A plus B plus C is equal to 0 minus A plus C is equal to 1 upon delta Z. A plus C is equal to 0. So if I write that in matrix form, then that matrix form will be 1, 1, 1 for 1 into A plus 1 into B plus 1 into C. So 1, 1, 1 into A delta G I have multiplied on both the sides of the equations. So A delta G, B delta G, C delta G as column vector. Then the second is for A it is minus 1, B is 0, C is plus 1. Minus 1, 0, 1, 1, 0, 1. That will be equal to on the right hand side, since I have multiplied delta G on both the sides. So right hand side will be 0, 1, 0. So right hand side is 0, 1, 0. So from that I can find out what are my coefficients ABC. Of course, it is very easy to find out. You need not use the matrix. Why I am using matrix is just to give a glimpses of how to use MATLAB. Because you know what is MATLAB. If you are using MATLAB, what is to be done. But otherwise it is easy, you can find out what is this B is equal to 0, what will be A, what will be, everything can be calculated from this. You don't even require pen and pencil. So let us see the MATLAB code for this, like this. So come to the MATLAB screen, if you have MATLAB, come to the command window. In the command window, write this command. So for the first matrix is 1, 1, 1. Then minus 1, 0, 1, that is the second row, semicolon, exclude, separation between two. 1, 1, 1 is the first row. Separation between two quantities by space is column or by comma is column. By semicolon is 0. So first row is 1, 1, 1, second row is minus 1, 0, 1. Third row is 1, 0, 1. That I have to left multiply with 0, 1, 0. Matrix in MATLAB, I have to multiply with 1, 0, 1, 0. So that is the parameter. So let me do that. If I do that in MATLAB, then you can see that the result is minus 0.5, 0.5, which means A is equal to 1 by 2, B is 0, C is equal to 1 by 2. I have used the transpose because in the first case, if I don't use the transpose, then there is a mismatch of element numbers. So they will not divide properly. I have to use the transpose of the rightmost side. So 1, 0, 1, 0 transpose that is this. And so from this, easily I get what are the coefficients of ABC, which means B is not required. If I am taking 3 points, the point where I am evaluating it, the point next to it on both the sides, then I don't require the value of the point where I am evaluating it. I will just take the other 2 points, the immediate neighbors of this point, and I can get the differences in value at the required point. That is what it shows. So based on this, we have different finite schemes, finite difference schemes. On the left hand side, I am showing you 3 schemes. On the right hand side, I am showing you the same 3 schemes. Difference is left hand side is first.
Sir, excuse me, sir. Excuse me, sir. Sir,
Yes,
audio is not clear. It's feeble, sir. The voice is feeble.
Am I audible now?
Yeah, it's audible.
Yes, there's a little bit low, sir.
Yeah.
Up to the previous slide, it was okay, sir. From this slide, your audio is little bit low, sir.
Let me try to correct it. Give me 2 minutes. Let me try to correct it.
இல்ல.
Am I audible now?
Yes, sir. Yes, sir.
The problem is here it is raining heavily. So network is giving severe problem.
Okay, no issue, sir. You can
That
continue.
is why I am getting into problem. That is one problem that I am trying to somehow manage from the money.
Okay, sir.
Okay, if it is now, let me share my slide.
Yes, sir.
Is it visible?
Yeah,
Is the
I
slide
think it's
visible?
getting loaded, sir. Yeah, it's getting loaded, sir.
Okay.
Yeah, it's there, sir.
Is there?
Yeah, it's very clear, sir.
Okay, let me change the slide and please tell me if it is changing.
Okay, okay, sir. Yeah, it's changing, sir.
It's
Yeah,
changing?
yeah. Yes, sir.
Good. Thank you.
Yeah,
Thank you.
it's changing, sir. Okay, sir.
Somehow it worked. Okay, this is now in these equations that you know, most of you must be knowing that. The first one is forward difference, the backward difference, the third one is central difference. And we saw right now, if I take 3 points, then the central difference is the best scheme. Uh, whether it is for time domain, whether it is for the time, or whether it is for the space, the central difference is the best scheme. This is apparently, it seems to be correct, but it is not correct. That we'll see later. If time permits, I'll show why it is not correct. But apparently, it seems that central difference is best scheme. What we do usually is we take a combination of that. Central difference in the time domain and either forward or backward difference, depending on who is using it, either forward or backward difference for the spatial domain. Sometimes we used to do that. Sometimes people use central difference for both the cases, but that has its advantages and disadvantages. Let me go to the next slide. Now, since is it, is it visible? MATLAB function to solve
Yeah.
differentiation.
Yes, sir. Yes, sir.
Excellent, excellent. So now let me write a small function. This is a function. So if you have MATLAB or you are using MATLAB, you can use this function. Write a script file or function. So go to the script window, not in the command window. Go to the script window. You can do this in the command window also, but it is better to go to the script window and write this function. This is actually being used to solve a differential equation in time domain. So I have differentiated uh, I have used numerical method for the differentiation of the spatial domain. So I will not touch that. I will use the differentiation of MATLAB to solve using MATLAB program the time domain. So what I am doing here is writing this function d dt means this d upon dt. So that is what you will get d upon dt of e. So if I am going to use e, d upon dt of e. So that is on the left side. That will be the thing that will come from the function. So that is equal to d e dt. d e dt will be the name of the function. So d by dt of e. That is why d e dt I have given it. And that is a function of E and E. Field, electric field E and E. So it can be anything. It can be E, U, X, Y, anything you can use. I am using it E for convenience. So that remains as it is. Then what is the size, step size? I am taking small step size. So DJ is the step size that I will calculate over one period, whole one period. So 2 pi is the period, one period over which I am calculating the step size. So now let me find out what is the step type. Total length is 2 pi divided by length of E. Length of E means the number of elements that is available in E, which means at how many points I am going to calculate E in the G direction. So in the spatial direction, total number of points where I am calculating E. So if I define E earlier, first, then that will be, which I can find out what is the length by using this command. Length of E is the length of the matrix. Length with bracket write any matrix that gives you the length of the matrix. Size, write a matrix that gives you the size of the matrix in the MATLAB. So if I know what is the total period, what is the total length, and how many points within that length, which comes from the length is, then I can find out what is DG. So that is DG. Then one is I've written percentage, DE, DZ. That is a commented line, comment out. So these two lines I am going to use. Now, since I will use the second one, I have commented the first one. I can use the first one by commenting the second one. Both are almost same, except there is one small difference that you can see. DETZ is equal to, you can see E2N, comma E1 minus En, comma E1 colon N minus 1. What does that mean? This is implementation of the central difference scheme. Now, in the central difference scheme, what we do, if I go back to the previous slide, but how I am doing the central differentiation, it is EY Z plus delta Z. So that is the first term. So that is where we are going to find out, and EY Z plus delta Z. Now please remember, delta Z is equal to dz. In the program, we are writing delta Z is equal to dz. And now that is fixed. What is changing is Z. So since I am taking a complete domain along the Z axis, so Z will have different points. So E is a matrix which is a 1 cross 100 matrix. Let us take it as a 1 cross 100 matrix or 1 cross 30 matrix. So EY Z plus DZ will be a 1 cross 100 matrix. Similarly, EY Z minus delta Z. So what does that how to implement it in the MATLAB program? That is what I have shown in the next slide. So this slide shows how I am implementing it. The first part is E2 colon N, which means I leave out the first element, second element to N, comma E1, then the first element, that is my EZ plus delta Z. Then the second is EZ minus delta Z. It started, the first one ended at E1. So the second one will start at En. So the second one will start at En. So that is why that has come. They have changed their position. En, and first one started from 2, went up to N. Second one is starting at 1, going up to En minus 1. So matrix number of elements in both the matrix matches. So that divided by 2 times dz. That gives you dE dz. And then ddt is equal to minus dE dz. So that will be ddt means what is going to be returned from this function. So once I write this function, then let us examine the effect of this finite differences. Now to examine, we know now how to write the function. We have written the function for that. For differentiation, this is my equation which I am differentiating. This for discretization, I write this in the discretization mode as dot ey is equal to right hand side, left hand side. Time I am not touching. Time it remains as d by dt. That I am not touching. That I will solve using MATLAB. So that remains as it is. Right hand side I am using here. Let me use the backward difference equation. Right? So that will be easier. I showed you the central difference equation. So in the same equation, go back. In the same program, if I want to see program, So look at the line that I have commented out. That is for the backward differentials. So that I am using. So it will be easier for you to understand both the things. So if I do that, we can understand both the things. So once I will use this, then I will use the second one. So for the starting, I am using the first one, which is commented. So uncomment that, go to the second one, comment that, and add on it. So next one. Okay, so this is my equation. This is now this is up to a first order approximation. What I have done is I have gone up to first order approximation. I am not gone beyond first order approximation. So with the first order approximation, what is the problem that we face that we are going to examine? Now, with the first order approximation, we have two terms: EYZ minus delta Z and EYZ. EYZ minus delta Z, that I can write as using Taylor series in the first order approximation in this form. Then the higher order terms I will neglect. So red part I have struck out, which shows that those errors are there inbuilt into my program because I have neglected them. And then my DTEY will be equal plus this side, left side, that I can bring to the right side, I bring to the left side, DTEY plus whatever is in the first line. So that will be equal to 0. DTEY plus V dou G EY dou G EY. We have found out an expression. So that will be equal to 0. Uh, so if that is equal to 0, let me take V is equal to 1, which is velocity is equal to 1. That is for simplicity. Also, I can take C0, I can take C0. But if I keep it at 1, it will be easier to understand. Now, what you see here is, now if I use this value, V dou Z dz and EY minus del Z square by 2 dz EY by delta Z is equal to 0. So then DTEY cross dou Z EY is equal to dou Z by 2 dou Z EY. So from that we get this equation, which is a second order term. The second part on the right hand side is a second order term. Actually, what we have done is, or what is being done is, actually in the numerical method, the moment we implement it in the numerical method, we are actually implementing a modified equation, not the first equation. Dou TEY is equal to minus V dou ZEY. That is the equation that we started. So dou TEY plus V dou ZEY is equal to 0. From that equation, we should get that equal to 0 on the right hand side. But because of the approximations, then we get the second order term. For second order approximation, we get so for first order approximation, we get a second order term on the right hand side. Beyond that, everything is 0. That is the modified equation, numerical equation. Actual equation is the above one. Now, what is the effect? What is the effect of this? The effect we'll see just now. To see the effect, what I will do is I will take EY to be of the form f x minus vt. As you know, any wave function, if you have a wave function, if you have a wave propagation, the function that represents wave function, a wave propagation, is of the form f into x minus vt or x plus vt. F can be any function. All functions of this form will satisfy wave propagation. That we know. Now, same thing, let me use for examining the FD, finite difference. If I do that, I am not going to spend time on Taylor series. I'm not going to spend time on Taylor series. Let me only say that now let us consider the effect of the third term. Second term we have seen numerically what is happening, or analytically what is happening second term. Let us consider the third term. So for this also we'll take the same equation, but what happens here is, instead of taking dou t ey plus dou g ey. I am taking the third order term expression, dou g ey, or dou uh, third differentiation of ey. Why I am doing that? Look at the last equation. From the first, second, third, fourth. Look at the fourth equation from the top. If you look at the fourth equation from the top, you can see that the right hand side is dou t ey plus dou g ey. That is what I require. Then in addition to that, there is dou g square by 6 third differentiation of ey plus higher order terms. I am leaving out the higher order terms. Now this means that I know the effect of dou g ey. So let me not consider that. I will consider only what is the effect of the last term. So if I want to consider the last term, how it is affecting the time propagation, so I will take dou t ey plus third differentiation of ey is equal to 0. For that, as I told in the previous slide, I will take ey to be of the form at t is equal to 0, it will be of the form e to the power jkz. You can take sine, you can take cos or any function. For simplicity, I am taking e to the power jkz. And you know, any function, if it is periodic, you can use Fourier transform, sorry, Fourier series of this form, exponential Fourier series, represent any other function. So if it is valid for this, it will be valid for any other function. So Ey is equal to e to the power jkz. Now differentiate that with respect to time on both the sides. Nice, sorry. Differentiate the right side with respect to space, with respect to z 3 times, because I have dou q ey by dou zq. So differentiate it 3 times, that will give me minus jkq into ey. So dou t ey will be equal to minus jkq ey. So if I solve that, then ey will be, this is a ordinary differential equation in time. Solve that ordinary differential equation in time. So that will give me ey as e to the power jkz into e to the power jk q times t. So from that, I can write it as e to the power jk into z minus k square t. This is very important. So ultimately, I am going to ey is equal to e to the power jk into z minus k square t, if I am adopting a numerical sleep. Now, what does this imply is the velocity or wave number, instead of being kt, is now becoming k square t. So it is increasing, which means higher order terms, high frequency terms will be prominent now. High frequency terms will be traveling at a faster rate compared to low frequency terms. And if del g square by 6 overcomes that, then they will travel towards the left because that is dominating. So it will not travel at that speed. If it is not dominating, then it will travel to the right. The same thing, I am doing the analysis, same e to the power jkz, I am putting for ey. Then in the difference equation, I am putting it for ey g plus delta z and ey g minus delta z. So if I put that value, ey g plus delta z will be e to the power jk g plus delta z. So from that I take e to the power jk z common, that e to the power jk z into e to the power jk delta g minus e to the power jk z e to the power minus jk delta z. Take common e to the power jk z. So that if I take common, other part is e to the power jk delta z minus e to the power minus jk delta z, which is 2j sine k delta z. So the denominator there is a 2 term, so 2 will cancel out. J will remain as it is. E to the power jkz is ey, so ey term will be there. This term actually, if I solve it, appropriate solution should give me, exact solution should give me, though Z EY is equal to JK EY, where K is the wave number. Now numerical solution is giving me J sine K delta Z by delta Z EY, which means K is being replaced by sine K delta Z by delta Z. This number is modified. K, the number original wave number, is being modified. Therefore, this term sine K delta Z by delta Z is called the modified or numerical wave number. We will see a MATLAB program. Let us see a MATLAB program for that. What happens there? What we have done up to now is we have written a function, simple function for differentiation in time using, and that we'll use now to solve the differentiation. So to start with, let me initialize E. So E0 is the initial value of E. E0 is equal to 0. I'll take 100 values to start with. I'll take 100 values. So it will be zeros of 100, comma 1 means it is a single vector, one row vector. Then I will put my source or whatever is the field, initial field. So initial field, let me take it as 1. E0 is equal to 1 between the time steps or between the spatial steps 40 to 60. So E0, 40 colon 60 is equal to 1. So there it will be 1. So I will get a square wave in that region. Otherwise, outside that 1 to 100 everywhere it will be 0, except between 40 to 60, where it will be a square wave. And that square wave is supposed to propagate. That propagation will come from the solution of the time domain equation. So the solution, let me get the solution. TE is equal to ODE45. ODE45 is a function available in MATLAB to solve ordinary differential equation. I have brought it into an ordinary differential equation form. dEy by dt is equal to some function. It is no more. On the right hand side, it is no more dEy by dz. For that, we have replaced and we have written a program, written a function. So that function is ODE within bracket at dE dt. dE dt is the function that is going to be integrated or solved, differential equation that is going to be solved. That we have already written. Which is the length? What is the length or limit? Limit is from 0 to 2 pi. So 0, 2 pi, that gives you the limit over which it is going to be solved, or the boundary. Left to right, that boundary is given by 0 to 2 pi. And with what initial condition that we have defined is 0. So with that, once I click or enter in the command window, I will get a solution. But since I have given a semicolon, I will not see the solution. Since I am not seeing the solution, I want to see what is the solution. So let me write plot E prime. E prime is the transpose of E. The moment I get that, I get a plot like this, in which it is on the y-axis I get the value of the field, and the x-axis gives me the z. So how the z is increasing from 0 to 100 or 0 to 1000, whatever I will take. I have taken here from 0 to 100, so 0 to 100. Now you don't get any information from this. The moment you look at this, it is just like blowing up, but you didn't get any information from this. Since I'm not getting any information from this, let me do something else. So I will plot it at the end. So not over the whole period. Let me plot it at the end. So plot E end, colon means all values of E at the end. So for all E at the end. So if I give that, then you can see what has happened. We, as I told you, we started initialized with a square wave. A square wave, why we took a square wave? It is almost like an impulse, and it contains almost all frequencies. If you take a square wave, theoretically it contains all frequencies programmed in nature. We started with that, but by the time we reach the end, You cannot say that this is a square root. This is completely gone. Out of proportion, it is no more square root. It is some zigzag functions. What is actually happening here is we are seeing high order terms, high frequency terms are here clearly visible, as well as there are dissipations. So instead of square wave, it has come down to be something like a Gaussian wave, and its peak is no more 1, it has come down from 1, and it is something like this. So this is not an acceptable solution. We do not require this type of solution. We'll see what are the remedies that we require. But please remember that this is what happens when you are using any commercial solver without knowing why you are using that. This is the solution that you will get. You will not know that you have got a wrong solution. You will use it and come out by saying that, okay, I have got a very good result. Because you use this solution in your result, your commercial software will use this solution to calculate or give you result, whether it is radiation pattern, whether it is input impedance, or that will be given by this solution, not the square wave, or not the original excitation initial wave that you get. That needs to be maintained, that is not maintained. And this is what happens because of the approximations, unless we take proper precautions. Precautions we will discuss later. Now let me see at what happens at the point 10, not at the end, somewhere between just before that. Now if you look at this, this is almost like a square wave. Look at this, take a close look at this. It has started to deform. It is not exactly a square wave. It has started to deform. So as you go away from the source, so it is starting to deform. Let me see at another point, point 50. So if I see at 50, this is very, now you can see what is happening actually. What is happening is very clearly visible here. If you look at this, there is ringing on the top and on the bottom, at the two edges. At the right edge, the ringing is on the top. On the left edge, the ringing is at the bottom. Now these ringings are actually high frequency components which are traveling, and you require this high frequency component to be present in your solution instead of decaying them. There are many programs, many commercial softwares. You also can use many other things by which you can add a decaying term, just multiply e to the power minus k as e, that will, and k is a real number that will decay. So you lose the waveform, original waveform will be lost. We do not want to lose the waveform. It is, we can bear with higher frequency term. This is what is called the dispersion. By dispersion, what we do, high frequency terms or different frequency terms are shifted to different locations. So Z is equal to 1 will contain a frequency term, Z is equal to 2 will contain a different frequency term, Z is equal to 100 will contain a high frequency term. So low frequency to high frequency, they will be distributed over the whole length. So that is acceptable because energy is conserved there. Otherwise, if you dissipate them, then we will not have conservation of energy, so that will create a problem for us later. So we do not want that. Mostly we do not want that to happen. So I will not advise anybody to use this dissipation. Rather, go for the ringing effects due to dispersion, because at least energy is conserved. Energy should not be. Instead, we'll see that when we go to the modulation. So let me see it once more. Instead of taking 100, let me take 1000 points. So if I take on 1000 points and give me my pulse is from 400 to 600, same procedure I am following. Then I am using OD solver and I am looking at the end. I'll look at the end now. Now you can see this does not show any any type of what you can say. Okay, but does not show any dissipation. So the wave is maintained almost. It is maintained rectangular pulse shape is maintained at the end. I am looking at the end. So even at the end, it is maintained. What has happened is high frequency terms are appearing in this towards the end. Towards the so at each grid point, at the end grid point also, it contains some high frequency term with which we will be okay. That is not going to affect your result. Net result will not be drastically affected if it contains high frequency term. But if energy is not conserved, conservation is not there, if there is dissipation, the square wave is completely vanished, or it comes to a triangular wave or some other thing, then that is not an acceptable solution. So those are certain things that we have to take into consideration when we are designing a numerical method, suitable numerical method. So this is for the finite difference span. High frequency terms are appearing at the end. Why this behavior is appearing? I don't know if I have that right now on that picture. So as I told you earlier, we find out an effective wave number, or numerical wave number, or effective wave number Kz, which is sine Kz by Kz. So if I plot that, then what I will get is something like this. Right. We'll get a sine curve. Now, from this sine curve, what I infer is as I keep on moving towards right, sine curve is between sine k delta z. So k delta z is on the x-axis is kz, y-axis kz. So that is the ideal condition. Proper solution should be axis is kz. But due to numerical solution, we are getting a sinusoidal distribution. Now, what we will require in the design of the method, FDTD method, is that this sinusoidal waveform should follow that 45-degree slope straight line to the extent it is possible. If I draw a 45-degree straight line and draw this line, this then they will deviate. Deviate means this curve, sine curve, will come down from the straight line curve. Now, what is the implication of that? That means the speed is going down. Wave number is going down compared to kz. It is falling down. So that they will, on the higher order terms, for higher order, high frequency, the speed will be slow. So the wave will propagate with slower speed as you keep on increasing the frequency. Numerical frequency. Remember, I am not talking about the physical frequency. We are doing a numerical simulation on numerical frequency. As we keep on increasing the frequency, this will be going slower, or so it will be decreasing. That we do not want to. We want to develop schemes where this line, 45-degree line, should match the sinusoidal curve initial part of the stem possible. Now, based on that, whether it matches to a large extent or a small extent, but based on that, we find out what will be our design. So the portion up to which it matches, find out that portion. So that gives me my kz, in which the numerical wave number and original wave number are same. Where they match, they are same. So that is the region which is of interest to me. So if I choose that region, from that I find out my dz. So from that I determine my what will be my z, or what will be my grid separation. Then the question of numerical dispersion and numerical dissipation is reduced substantially. Of course, dispersion is reduced, or dissipation remains as it is. Dissipation comes from different angle, not from this. But this is basically for dispersion. So that is how you choose the grid separation in the spatial domain. Then comes the time domain that we will discuss later. But let's first start with grid separation in the spatial domain. For that, this is what you should know. Once we know that, if you know your software commercial package, and what is this, how much they are matching, KZ uh, uh, ideal and KZ due to the numerical method that they are using in the software, how much they are matching. Accordingly, choose your DZ, then your result is going to be less dispersive. It is going to be more accurate. Of course, we have to see what order they are using for approximation. I remember this also. I think it is up to tell it here. The order is, if you take odd numbers, odd order, then it will be dispersive. That results in dispersion. If you take in even number, that results in dissipation. So try to avoid even number. Try to go for odd number. By even number means, so what I mean is truncation. When you are truncating, truncate at an odd number, not at an even number. If it is even number, you'll be getting into problem because there will be dissipation. So no conservation of energy in the numerical scheme. Okay, this shows okay. Again, same plot with grid. This shows the grid for the same plot. I don't know. I think if I get time, I'll come back to this. Give me 2 minutes. Let me take some water. Actually, I am having fever for last 4 days from Monday. So I'm getting tired. Let me
Yes,
take some
sir.
water.
Okay.
Now, how are you, sir?
I am having fever, but I can manage. I committed. If I make a commitment, I usually honor it. So this is what we discussed is about the basics. So let me skip this because I don't have these slides, proper slides. I have missed somehow today because my laptop was, I have to reboot it, restart it. So I have lost many slides. Some slides are there, some slides are not there. If I get time tomorrow, I will get discuss that, those questions. So leave it up
Sure,
to you.
sir.
Leave it up.